Hello everyone. Today I'm going to talk about our paper, Adversarial Ranking Attack and Defense. Deep neural network classifiers have been found susceptible to adversarial perturbations. Such perturbation is imperceptible to human and can cause misclassification. As shown in the figure, when a slight adversarial perturbation is added to the panda image, the decision of the same neural network has been changed. Such phenomenon poses reliability concerns on deep neural networks. However, although the vulnerability of deep classifiers have been extensively explored, the vulnerability of deep ranking systems remains underexplored. So in this paper, we propose adversarial ranking attack, which is defined as to raise or lower the ranks of a set of chosen candidates with respect to a specific query set. This can be implemented by two kinds of attacks, candidate attack and query attack. The candidate attack changes the candidate ranks by adversarially perturbing the candidate images, while the query attack changes the candidate ranks by adversarially manipulating the query images. Let's look at the right side diagram. For example, there are 5 rows of retrieval results on the shopping platform using images of a white lamp. The first row is the original retrieval result. Let's consider a malicious seller who wants to raise the rank of his own product, namely the one enclosed by a dotted red box, ahead of all the rest similar products. This is called CA+ attack. Besides, a malicious seller may also want to lower the rank of the products from its competitors. For instance, the product enclosed by a blue dotted rectangle. This is called CA- in our definition. On the other hand, we can also change the candidate ranks by modifying the query images, which is called query attack. In a real image ranking system such as shopping platform, a man-in-the-middle attacker may leverage query attack to promote or impede the sales of some specific products. Then, given the attacking goal, how do we achieve it? Now let's recall the deep metric learning for ranking, since ranking is a direct application of metric learning. Deep metric learning aims to learn a distance function between sample pairs. Typically, it involves learning an embedding space with the triplet ranking loss, where similar samples are projected close to each other, while dissimilar samples are projected far away from each other. Given such an embedding space and a query image, we can sort the candidates according to their relative distance to the query embedding. In such a framework, how do we perform adversarial ranking attack? Taking candidate attack plus, for example, in this case, we attempt to raise the rank of a specific candidate image by adding adversarial perturbation to it. So we turn this goal into a series of triplet-like loss functions and find the perturbation with projected gradient descent. Similarly, for CA- and query attack, the way of finding the adversarial perturbation is more or less the same. However, for query attack, simply applying this idea may cause a problem. Let's take QA- as an example. In this case, we attempt to lower the rank of the chosen candidates by adversarially manipulating the query image. By simply using the naive QA- loss function, we can indeed accomplish the goal. But as a byproduct, the semantics of the query image may be greatly changed, leading to abnormal ranking results. This is an undesirable phenomenon, and the users could immediately identify the anomaly. So can we keep the query semantics to avoid such phenomenon while achieving our attacking goal? Our solution is simple and straightforward. We select the original top K candidates as ground truth and put them in the QA plus loss function as a semantics preserving term. Then we append this term to the attacking loss. We call this semantics preserving QA minus. So during the optimization process, we do not only lower the rank of the selected candidates, but also raise the rank of the ground truth candidates. In this way, we can make our attack stealth and avoid raising alert from the user. Now let's look at adversarial defense. The previous works about adversarial defense mainly focused on the classification task, and most notably, adversarial training is one of the most effective defenses so far. To adversarially train a neural network, the training dataset is augmented with the adversarial examples. However, the previous methods cannot be directly adopted for the ranking task, because ranking has a different training loss function compared to classification. Besides, a single defense performs differently against different attacks. So, in this paper, we also propose an adversarial defense dedicated for ranking system. Recall that the underlying principle of our proposed attack is to shift the embedding vectors in the embedding space by adding adversarial perturbations. And a successful attack depends on a large embedding shift distance and a correct shift direction. Based on that, we propose a maximum shift distance attack for generating adversarial examples for adversarial training. To verify the effectiveness of our proposed attack and defense, we conduct experiments on the toy dataset MNIST. Let's take CA+ as an example. Given a query image, we randomly sample a candidate image and we want to raise its rank. Without any attack, the randomly selected candidate is ranked at top 50%. But after performing CA+, with a perturbation budget 0.3, its rank is raised to top 2.1%. Then, we train a model with our defense. As shown in the second table, the strongest CA+ attack can only raise the rank from top 50% to top 30.7%, which means the attack effect has been significantly reduced by our defense. We also performed the attacks on the Stanford Online Products dataset, which includes product images from the eBay platform. This is a realization example of our CA+ attack. Our candidate image is a chair, which is ranked at 3737. After performing the CA+ attack, it is ranked at the third place given the same query image. This is an example of QA-. Our query image is a lamp, and we want to lower the rank of the 7th candidate lamp. After QA- attack, the rank is lowered to 782 given our adversarial query. Here are more examples of our 4 types of attacks. Here are some examples of our CA+ attack with 2 different query images. In the left example, our candidate image is a blue bike, while the selected queries are a yellow bike and a red bike. After CA+ attack, it is ranked ahead of nearly all the other bikes given any of the 2 queries. We can also perform QA+ attack with a set of candidates. In the left example, our query image is a cabinet. We select the candidates ranked at 1512 and 1620. After the QA+ attack, the ranks are raised to 8 and 1 respectively. This is a final example of CA+ attack with a query set containing 10 different query images. All these results demonstrate that our attack still remains highly effective when the difficulty is increased. More high-resolution results and more details can be found in our preprint paper. Okay, I hope my presentation is inspiring or helpful to you. Thank you for watching.